Last video, we broke down the transformer, the architecture that replaced recurrence with attention. Now let's trace what actually happens inside GPT when you type a sentence and hit enter. The first step is tokenization. Your text gets chopped into small chunks called tokens, which might be whole words, parts of words, or punctuation. GPT doesn't see letters or words the way you do. It only ever sees this list of tokens, each one just an ID number from a fixed vocabulary of tens of thousands of possible pieces. Each token ID is then converted into an embedding, a long list of numbers that captures something about that token's meaning, learned during training. Position information gets added in too, so the model knows not just what each token is, but where it sits in the sequence. Exactly the positional encoding step we covered last video. What comes out of this stage is a stack of number vectors, one per token, ready to be handed to the transformer itself. Those vectors flow up through GPT's stack of decoder blocks, the same self-attention, feed-forward, and residual connection pattern we detailed in the last video, repeated dozens of times. Every layer lets each token refine its understanding by attending to every token before it. By the time the vectors reach the top of the stack, each one carries a rich, context-aware representation, not just of its own token, but of everything that came before it in the sequence. The final layer takes the last token's vector and turns it into one score for every single token in GPT's entire vocabulary. Tens of thousands of numbers. A softmax function converts those scores into probabilities that all add up to 100%. In plain terms, GPT isn't looking up an answer. It's computing how likely each possible next token is, given everything it's seen so far in the conversation. GPT then samples one token from that probability distribution to actually output. It usually doesn't just grab the single highest scoring token every time. A setting called temperature controls how much randomness gets mixed in, which is exactly why the same prompt can produce a slightly different answer each time you run it. This is also the root of hallucination. The model is always producing a plausible sounding next token, not consulting a database of verified facts. Here's the part that makes GPT feel like it's writing rather than just answering. That newly sampled token gets appended to the sequence, and the whole thing, your original prompt plus every token generated so far, gets fed back through the entire model again to predict the next one. One token at a time, in a loop, is literally how GPT produces every sentence you've ever seen it write. That loop can't run forever on an unlimited amount of text. Every GPT model has a fixed context window, a maximum number of tokens it can hold and attend to at once. Once a conversation grows past that limit, the oldest tokens fall out of view entirely. The model literally cannot see them anymore, which is why a long chat session can suddenly seem to forget something you said near the start. For security work, this token-by-token, probability-driven process explains a lot. Because GPT always predicts a plausible next token rather than retrieving a verified fact, it can generate convincing text that's simply wrong. And because instructions and untrusted input both just become tokens in the same context window, an attacker can smuggle in text that reshapes what the model does next, the basis of prompt injection. The same fluent text generation also makes GPT-style models a tool attackers use to write phishing emails and scripted social engineering at scale. So that's the full loop. Text becomes tokens, tokens become embedding vectors, those vectors flow through a stack of transformer decoder blocks, the final layer produces a probability distribution over the entire vocabulary, one token gets sampled, appended, and fed back in, again and again, until GPT decides it's done. Understanding this pipeline is what lets you reason clearly about where these models are reliable and where they are not. Subscribe for more AI and ML foundations built for security people.